Hello everybody, welcome to Chapter 2.6. Today we're talking about derivatives of inverse functions. And what we're going to talk about are how to find derivatives of inverse functions, and then also we want to understand that derivatives are reciprocals between functions and their inverses. What's really cool about this is that we get to take a closer look at things we already know about inverses. But before we do that, let's do some formal definitions real fast. It's always a good idea to do those. We're going to talk about continuity and differentiability between inverses and their functions. So, just a few math speak things for you. If fancy f is continuous over its domain, then f to the negative 1, its inverse, is also continuous over its domain. If fancy f is differentiable on an interval containing c and f prime of c is not equal to 0, then f to the negative 1, the inverse, is differentiable at f of c. Okay. So just some basic things about continuity and differentiability that we should understand. Good rules for us to have in our notes. The next thing I really want to talk about are the ideas that reciprocal slopes happen because we have reciprocal derivatives, or I should say reciprocal slopes mean that we're going to get reciprocal derivatives between functions and their inverses, and here's a quick demonstration as to why. If we take a look at some make-believe graph, let's use this as our coordinate plane, and then let's make, I'm not sure, make some curves here. Maybe this is our function f. Then here's the line xy. We remember from chapter P4, our review of inverses, that the inverse, the f to the negative 1, will reflect f over that line xy. So it'll look kind of like this. And it's also important that we understand something. So any point that we have on our line of f, any point x, y, will have that same value for y and x, but switched for our inverse. So instead of having the x and y, what we'll have is that point on f to the negative 1 on our inverse. We'll have it first reflected across the xy axis, the xy line, and our point there will be the value of y, x. And again, that makes sense because the domains and ranges switch for functions and their inverses. So every point x, y we have on this line, we have a same point over here, y, x. Okay. And furthermore, what we can talk about next is the concept of tangent lines. So here's the tangent lines through the point x, y on our function f. And then here's the tangent line through the point the corresponding point on our inverse. So for example, we can give this a number. I feel like that's confusing to just throw that at you, so let's do this instead. Okay, let's throw some numbers in here. So we'll call this one officially 1, -2, and since that's a point, that means that -2, 1 is a point on this graph. Okay, now that we have some numbers, I feel like that makes a little bit more sense. Okay, and what we're going to talk about now is the idea that since they have reciprocal slopes, they have reciprocal derivatives. And that makes sense because let me use green, there we go, okay. If we had 2 points on our tangent line, so we have the point, let's say xy, and then we had the point x2, y2. To find the slope of this, we would have y2 minus y1, so slope of f would be y2 minus y1, or y2 minus y, over x2 minus x. Similarly, over here, if we had some other point on the tangent line going through our inverse, then what we could call that point, since it's reflected over the xy line, since its domains and ranges switched from the other tangent line, we could call this point y2, x2. And so the slope of f to the -1, we could find that, I should say prime, and I should say I actually forget I said prime. We are just talking about the slope of f here, so just the slope of this tangent line, the slope of f at that point. We could find that by looking at this point and this point on its tangent line, and then finding the slope at that tangent line. And we could find that slope just theoretically by doing y2 minus y over x2 minus x. And then to find the slope of the inverse line, we would do the same thing, but now our y's, the things we need to put on top, are represented by the x numbers, right? The x2 minus x, and then we would say minus y2 minus y. And now we can see very clearly what's happening between these two functions, the inverse and the original. The original has y2 minus y on top. The inverse puts that on the bottom. So they flip each other. They're the reciprocals, and that is true of any function and its derivative. Any function and its inverse for their derivative. Okay. Yes. Okay, and then from that discussion, what we can arrive at is the theorem of reciprocals, or pardon me, the theorem of inverse derivatives. So, the theorem goes like this. It says that g prime of x equals 1 over f prime of g of x, where g is the inverse function and f is the function. It's the function you start with. Okay. And again, that makes sense because we're talking about the concept of reciprocals. So what we can do is we can apply this theorem in an example that looks like this. We can say let f of x equal 3x cubed minus x squared minus 8. And we're asked to find f to the -1 of x and f to the -1 prime of x. So the inverse of the derivative of the inverse when x equals 12. And we can begin this first by identifying what is going to be 12 from our original function. And here's what I mean by that. Remember that if you have a point f of a equals b for your function, then you most definitely have a point f of b equals a for your inverse, right? The domains and the ranges switch. So what we can do is we can use this information. What we can do is we can find the y value, the f of what equals 12, right? And we're going to fill in this blank by looking at a graph. So if we turn on our grapher, we go to y equals, and we put that in there. I've already put it in there, but we have 3x cubed minus x squared minus 8. And we graph it. This is zoomed way out, first of all, so I'm going to go to Z standard to make it a little bit easier to see. And what we can do here is, it's kind of hard to see exactly where our function is 12. What we can do is we can go back to y equals, we can graph y equals 12, and what we can do then is, let's fix our window for a second actually so we can include that 12. Let's make our max like 13. Okay, there we go. Now we can see it at least. There's 12. We can see where these two intersect each other, where our graph intersects with the y value of 12. If we go second trace and we go down to intersect 5, we want to see where it intersects this line and our line. We want to see where they intersect each other. Okay. And we press enter again. And it looks like they intersect each other. Our function is 12 when x equals 2. So I fill in the blank here with a 2. Now that means the inverse, vice versa, of 12 is 2. And we found that again just by looking at that graph. And now we have our numeric solution there. Now to find the derivative of our inverse at 12, we can use our theorem. And here's how we could set that up. We would do 1 over f prime of g of x, which means of the inverse of the value, so of the inverse of 12. And what we can go do from here is say f to the negative 1 prime of 12 equals 1 over, well, we know the inverse at 12 is 2, so we can say f prime of 2. And we can find f prime by looking at our original function, right? We can just write this in another color real quick. To find f prime, we take the dx of everything in there. Here we would get the 3 times the 3, so we would get 9x squared. We would get minus 2x, and we would get 0, so f prime is this. And now we're going to use 9x squared minus 2x in the bottom here. We're going to say f to the negative 1 prime of 12 is 1 over the derivative at 2. So 9 times 2 squared minus 2 times 2. 1 over 9 times 4 minus 4, or 1 over 32. And we have found everything that question is asking. Let's talk really quickly about the ideas of reciprocal slopes at corresponding points. All right, so let's talk about that idea. Let's put our topic at the top of reciprocal slopes with corresponding points. So what we can do here is we can look at when f of x equals x squared, and when f to the negative 1 of x equals square root of x. What we're going to be asked to do is we're going to be asked to show that the slopes of the graphs of f and its inverse are reciprocals at each of the following points. At 2, 4, and 4, 2, and at 3, 9, and 9, 3. Now it's important that we understand why these points are written like this. They're going to have those reciprocal slopes, but at the corresponding points. Remember that they're going to have reciprocal slopes where the two lines reflect each other, just like in our first example here. The slopes reflect each other at the points that the slopes are reciprocals at the points that reflect each other. So, for example, at 1, negative 2, and at 2, negative 2, 1, that's where the slopes would be reciprocals. Any point that's reflected over the xy, the line y equals x. Okay. Excuse me. To start this question off, it's going to be important that we understand what the derivatives of both of these functions are. So let's quickly identify f prime to be 2x, f to the negative 1 prime would be power rule 1/2 x to the negative 1/2, which would be 1 over 2 square root of x. And I got that because I put the x to the negative 1/2 on the bottom of the fraction because it was negative, and we remember the 1/2 is actually the square root of x. So those are our two inverses we're going to use to help us. Those are our two derivatives we're going to use to help us. My goodness. Okay. So let's say the slope at 2, 4 for one of these. Let's say for f prime. And then we're going to look at the slope at the corresponding point at 4, 2 for the inverse for f to the negative 1 prime. I don't like that I said slope just now, so cross that out. That shouldn't be there. We're looking at the 2, 4 for f prime and 4, 2 for f to the negative 1 prime, so we can see their slopes at that point. That's what I'm trying to say. Okay. Now what we're going to do is we're going to substitute in this x value to our derivative for f. And so what we do there is we say f prime equals 2 times 2, which is 4, at the point 2, 4. Now its corresponding point on the inverse is 4, 2, and so we want to examine f to the negative 1 prime of 4, and when we do that, we're going to get 1 over 2 times the square root of 4, 1 over 2 times 2, 1 over 4. And we can see that, in fact, 1/4 and 4 are reciprocals. They are inverses. They do what they're supposed to do. Let's look at 3, 9 for f prime, and let's look at 9, 3, the corresponding point for f to the negative 1 prime. So we can say f prime of 3 equals 2 times 3, which is 6. Now, knowing that, we know that we should get 1 over 6 here. Let's make sure that we do. F to the negative 1 prime of 9, well, that's 1 over 2 times the square root of 9. 1 over 2 times 3, 1 over 6. And once again, we can see that 6 and 1 over 6 are in fact reciprocals of each other, and we are good to go there. All right, that's all I have to show you for this chapter. We'll see you in class tomorrow.